All right, so this is Unit 4, Lesson 2, and we're going to be talking more about the idea of those rectangular approximation methods. In the first video that you watched, it was LRAM, MRAM, and RRAM in order to calculate the area under the curve. And basically what it's doing is slicing up the area into rectangles, and then just doing base times height and adding up all of those rectangles. Now, in the first lesson, we were dividing the base from A to B into equal bases, equal width rectangles. And at the top of this page, it says, although yesterday we learned systematic ways, that should say, to approximate the area under a curve, in theory, the intervals do not need to be the same length. So the intervals do not need to be the same length. Oh, hold on one second. My Apple Pen is not connecting. Let's see if that works. There we go. And the heights can be determined at any values within each subinterval. So the LRAM, MRAM, RRAM, we're going to be asked to calculate. It's a systematic way of approximating this area under the curve. But if we kind of take away, well, what type of problems am I going to ask you to solve? Theoretically, you can split up the area under the curve whichever way you see best fit. If there's a big block rectangle that looks like it takes up a good portion of the area under the curve, and then this one a little bit skinnier, the goal is really just to approximate the area under the curve. So each delta x, which are the bases, could possibly be different. And we would call that a partition. So for example, this one says this partition divides the region R into n strips, but you'll notice that they're all different delta x's. So this base in here, we could call this delta x1, is definitely bigger than this one would be my delta x3, and so on. And each of these bases are different. LRAM, MRAM, and RRAM are all specifically defined Riemann sums. So this idea that we could have any amount or any size base and any y value as the height is the idea of a Riemann sum, that we're going to add up all of these rectangles. Now, as our biggest rectangle then, let's look at our widest or the biggest base. As that value goes to 0, I'm going to pull up quick the Desmos calculator that we were looking at in the first lesson. And the idea of our biggest rectangle, even though right now these are all equal, as that goes to 0, what that means is that we're going to squeeze more and more and more rectangles underneath the curve. And what happens is the more rectangles we squeeze under here, if I move this slider all the way to the right, it lets me do 100. It really looks like it's just shaded perfectly under the curve. Now, when we scroll back and we see that we're really making rectangles, that's when the error in the approximation is showing. The idea is that as this goes to infinity, the number of rectangles underneath, we're actually converging to the actual area underneath the curve. So it says as the max, delta x goes to 0. So remember, delta x are the bases of our rectangles. So as that goes to 0, then that means the number of rectangles will go to infinity. We're going to make the base smaller and smaller and smaller to get more and more rectangles underneath the curve. Then the sum of the rectangles will converge to the actual area under the curve, the exact area underneath that function. So the notation for this is what we have to go over now. A Riemann sum is a limit. So the first part of this is the limit as n goes to infinity. So n going to infinity, This is talking about the number of rectangles. The base of the rectangles is going to 0, so the number of rectangles, n, is going to infinity. So this is our first part. It's the limit as n goes to infinity. Then we've got this summation notation. This is the sum from the first to the nth rectangle. This is the sum from the first to the nth rectangle. And then we've got this f of x sub I times delta xi. Now, that looks really complicated, but the f of xi, that's just your function evaluated at an x value, meaning a y value. That's the height of our rectangle. And then the delta xi, delta x, is just the base. We're just using that subscript I to represent a specific height times base. Height times base, or base times height, that's just the area of the rectangle. So this is really saying just add up all of the rectangles, their area, base times height, from the first to the last rectangle. So there's a lot of notation here, but it's really just saying add up all these areas. Questions so far? The big thing that I've added in front of this now is this limit as n goes to infinity. What we were practicing in lesson 1 was a finite sum. I was saying 5 rectangles, 4 rectangles, 10 rectangles, whatever it is. Now we're turning it into a limit as n goes to infinity, and this is what is going to introduce to us what the definite integral is. A definite integral is the next step in our journey learning calculus. It's our next derivative. Now we get the integral. It's its inverse. It's the next main idea in our course. And the definite integral is the area underneath the curve. The area underneath the curve is the definite integral. And I'm going to say that over and over again, the way I've always said that the derivative is the slope of the tangent line. The derivative is the slope of the tangent line. The definite integral is the area under the curve. So we've got this new fancy notation here. First, we've got this squiggly S thing. That's our integral symbol. We read this as, let's just fill in the notes here before we kind of label it. It says the notation is read as, so we read this as the definite integral from A to B. The definite integral from A to B. So notice that that's like from the bottom to the top, the definite integral from A to B. Then we say of f of x with respect to x. Of whatever f of x is with respect to x. That's the dx part of it. So when we're reading this, it's the definite integral from A to B of f of x with respect to x. That's that dx on the end. Let's label some of the parts. That A to B, those are our limits of integration. It's the beginning and end of our interval. So A, the interval from A to B, this is called the lower limit of integration. The lower limit of integration. And the B is then the upper limit of integration. of x, we would refer to that as the integrand, to kind of say that's the function we're taking the integral of. So if I say something referring to the integrand, that's the function that we're taking the derivative of. And then the dx gives us the variable of integration. Oops. So, oh, sorry. So just some vocabulary. When we say dx with respect to x, that's also giving us a visual that we're going to the x-axis. We're talking about the area under the curve. So we talked about how to say it, the definite integral from a to b of f of x with respect to x. But what does it do? And it can be used to determine the net area bounded by the x-axis and the function f of x. The net area bounded by the x-axis and the function f of x from x equals a to x equals b. That's the beginning and end of the space that you're looking at. All right, one more thing that I want to say before we kind of move on. When we go back up to here, where it's talking about the height times the base, I want to talk a little bit more about this x sub I and delta x sub I. First, let's talk about delta x because it's a little bit easier. It's the same that we did in the first lesson. The base, the delta x, is just going to be your b minus a divided by n. Even though theoretically the length of the bases can be any length, when we're going to be evaluating any of these examples, we are going to have equal bases in order for us to kind of interpret the notation. The I is just the base of the ith rectangle. Is it the first one, the second one, the third one, the fourth? The delta x, though, is sort of the base. It's the splitting up of the interval from a to b. Now, the xi, as you move along, you're going to be starting at a and then moving over the delta x each time to get the new x value. So when we're looking at this x sub I each time is going to be starting with a, the beginning of the interval, and then adding delta x however many times we've moved over. So times I. Starting at a and then adding delta x however many times we've moved over. That's going to be the x value that we're plugging in. There's a lot of notation to digest here. So what we're going to do on the back here is we're going to kind of bounce back and forth between the integral notation and the summation notation. Let me do one of them with you, and then I'll see where your questions are, because right now I feel like there's just a lot to look at, and let's do an example. So in the chart below, we have a definite integral that's been provided for you. We want to write the corresponding limit of a Riemann sum. So we want to write the limit as n goes to infinity. This is the same for all of them. The limit as n goes to infinity, the summation from, now I have I in the notes. Sometimes you'll see a k. So I want to change this one to K just so nobody's thrown off. I or K is just which rectangle you're at, the first, the second, the third, the fourth, or the ith or the kth, whichever letter they decide to use as their counter. All of our limits are going to start off with this notation. This is consistent for all of them. The limit as n goes to infinity of the summation from the first to the nth rectangle. Now, the first thing that you want to do, and I'm going to kind of squeeze it in here, the steps. First thing I want to do, step 1, is I want to find delta x. And I'm going to use that formula b minus a divided by n. So let's do that first. I'm going to look at the integral, and my integral is going to give me the a to b. So I can calculate my delta x, b minus a over n. So delta x is 6 over n. And it's always going to be in terms of n because remember, eventually n's going to infinity. That's the theory behind this. The second thing that I need to kind of put together in order to write the correct notation is I need x sub I, what we're plugging into the function. And that's that little formula that I'm going to take a, where I'm starting at, and add delta x, however many times we're using it. So on this one, since I've decided to be annoying and use a k instead of an I, a k, I just don't want you to get thrown off. They can use whichever letter you want. X sub k would be a, which in this case is 0, plus my delta x is 6 over n times k. So now what I can do is build my Riemann sum. Because now that I have delta x and xi, I can plug them in. So if I just scroll to the front page one more time, I need the height. The height is my f. The height is my f of xi, or f of x sub k, then times delta x. So the function this time is the square root of 2x plus 1. That's my f of x. So instead of an x, I'm going to be plugging in, and I really don't have to write 0 plus, right? So let's simplify this xk. Instead of an x, I'm going to plug in. So I'm going to have the square root of 2 times, instead of an x, 6k over n plus 1. So that was my function. And then times delta x, 6 over n. And this just wants the notation. The limit and the integral are saying the same thing. It's almost comparable to derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. The summation is the formal definition, and the integral is the notation, meaning calculate the integral. Questions? Jenna.
I just don't know where the k equals 1 is coming from, like on the bottom of the note.
That's always going to be the same because k or I is just your counter of which rectangle you're at. So it's always going to be of the first rectangle. So it's always going to be from k equals 1 all the way up to the nth rectangle, which would be the last one. theoretically that n is going to go to infinity, that we're going to keep getting more and more and more and more. So this 1 to n is just the counter of how many rectangles you're putting under there.
Okay, thank you.
Other questions? All right, so let's try another one and then we'll see as questions start to pop up, because I understand that sometimes it takes a few of these to figure out what your question even is. So let's look at the next one. We want to convert this integral into a Riemann sum. And the first part is not going to change. The limit as n goes to infinity. Oops. Should we use I or K? I. So we're going to say I equals 1 to n. So that beginning part is going to be the same for all of it. The limit as n goes to infinity from the first to the nth rectangle. All right, I need my delta x. So a is -2, b is 3. So my delta x, b minus a over n is 5 over n. And then I need my x sub I, which is going to start this time at -2. So it's -2 plus my 5 over n, and we chose the counter as I this time. So it's always going to be a plus the delta x that you just found times the counter. And now we're going to plug it into the function. The function is x squared minus 3. So where there's an x, I'm going to replace it with this whole x sub I. So I have in parentheses, and then parentheses around my x, -2 plus 5, and you can even put the I in the numerator with the 5, right? Times I could be in the numerator or next to it, squared, and then -3 is the rest of the function. That's my f of x with this crazy xi plugged in for x, times delta x, 5 over n.
The dx is the delta x, which in this case is the 5 over n.
Yes.
Okay.
Dx is the delta x. It's this change in x. Theoretically, when it gets to the form dx, it's that we are fitting infinity rectangles and the dx actually went to 0. But that's why it turns into notation. But it is the base. The dx is the delta x, or the small change in x. Questions? Let's do another one. The integral from 1 to 6. So my a is 1. My b is 6. Delta x, b minus a over n is 5 over n. And my x sub I is a, which this time is a 1, plus my delta x times I. All of my Riemann sums are the limit as n goes to infinity. I'm squeezing an infinite number of rectangles under the curve, starting with the first one and ending at the nth one. So the limit as n goes to infinity, the sum of all of the rectangles from first to last. I'm just waiting for my n to show up. Let's plug in for x. So my function is 3x minus 4. But x is going to get my x sub I. So I'm going to have the function 3 times 1 plus 5n over 1. Sorry, 5n times I minus 4. Because this is going to get me the height of whichever rectangle I'm in. And then times the base, delta x is 5 over n. Before we continue with these two, let's jump down and see how we reverse the process. I think it's going to help solidify kind of who's who and where everybody goes. If you look at the bottom table now, we're given the Riemann sum and they're looking for the integral. So when we're doing this one, the first thing that I want to do, I'll squeeze the steps down here for this one. The first thing that I want to do is find the a and the delta x, because they're visible in your Riemann sum. Remember, a plus delta xi is what goes in the parentheses. So this expression in here is my a plus the delta xi, but even more clear, in my opinion, is the delta x that gets thrown on the end. So in this first one, I know I'm looking at an a of 2 and a delta x of 4 over n. A is always the number in front of the delta xi, and delta x is always very visible at the end. Because once you know those two things, you can find b. Or actually, I should say calculate b. It's a simple calculation, but finding kind of implies that it's just there for you to look at. We actually have to calculate b. Because we can take a and add to it the b minus a that's visible as the numerator of delta x. Because remember, delta x is the change. So if we're going to start at 2, and then the difference between b minus a is 4, if we just add 4 to the 2, then we're looking at an integral that starts at 2 and goes to 6. Because if I now calculate b minus a, 6 minus 2 is the 4 over n. So you're just kind of putting it back to figure out what's the interval. Now what I need to do is figure out f of x. Find the function f of x, which basically means we're going to replace the a plus delta xi with an x, just a big old variable x. This whole a plus delta xi is really just the x of my function. And it's just trying to say for each rectangle it's moving us over. So the function is really 5x plus 7. And then, like Jenna said before, the delta x is the dx in the integral. There should never be any n's in the integral. N is going to infinity. That's what's making this become the definite integral. Let's try another one. The limit as n goes to infinity, the summation of, well, I'm supposed to find a, and in this one I just have 4i over n. What would that make a if it's just not added there?
1.
Good guess, but not 1, because I would have to see a 1 plus.
0.
0. A is 0. If there you don't see a something plus, then the only thing that's allowed to drop out is a 0. And then the delta x is that 4 over n on the end of this. So I'm looking at the integral from 0 to, well, just add together the 0 with the numerator of 4. That's going to be the interval from 0 to 4. That's what makes my b minus a over n 4 over n. Now look at my function. Instead of this 4i over n with all these crazy extra letters, I'm just going to make this my function of x. So my function in terms of x is 6x squared minus 2 dx. With respect to x is that delta x on the end.
How come in the xi the 2 isn't negative?
It should be.
Oh,
Good catch. All right, in class, it seems like everybody's at least had a chance to try all three. So I wrote number 4 up here. First, delta x, b minus a over n. Then xi, which is a plus delta xi, and built the Riemann sum. Questions on that one? All right, so our next one, the delta x, is b minus a over n. So 2 over n. And then the xi starts at negative 2 and adds the 2 over n times I. So the limit as n goes to infinity is always the same. The summation from I equals 1 to n is always the same. And now where there's an x, I'm going to plug in this crazy xi. So negative 2 plus 2i over n. And then it's squared plus 1 all under the radical. And then times delta x out of the radical, like that.
Please stand for the Pledge of Allegiance. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Please be seated. This week is Spirit Week. Tuesday is Patriotic, Wednesday is Sable Pride, Thursday is Trends, Friday is Costume. Get your spirit ready. Attention members of the Sable family. The senior class is looking for your support in our holiday wreath fundraiser.